Welcome. We're going to spend a few more minutes on types of energy, and specifically, we're going to talk about the E-Lab you folks just got done doing, the Energy Transformation Lab, where you were firing Trevor, the hockey player, across ice with a spring. And you were studying a bunch of things. You were studying how Trevor's velocity depended on the following three things. You changed Trevor's mass, you changed the spring constant, and then you changed how much you compressed the spring. Uh, so I want to spend just a moment talking about that and about the results you folks got. And this will kind of lead us into the last half of the unit, which will be talking about something called conservation of energy. So when you compressed the spring, you gave it elastic potential energy. You did work. Your food calories went into compressing that spring, and that energy was stored in the spring. That's what we call potential energy. So you start with E, elastic, all right? And then you launched Trevor. So what happened to that elastic energy? What did it turn into? Well, it made Trevor move. So that elastic energy turns into the energy of motion, which is called kinetic energy. Okay. Uh, so what I want to do is briefly talk about those two formulas that we know now, and talk about how that was involved in your lab. So you have elastic energy, which is 1/2 k x squared. Remember, k is a spring constant. That's newtons per meter. And x is the distance you stretch it or compress it in this case, and that's meters. And that's going to turn into Trevor's kinetic energy, which is 1/2 mass velocity squared. Okay. Now, in the lab, you were graphing velocity versus something each time. So what we're going to do is take this equation and solve it for velocity, get velocity by itself. Well, first of all, I can cancel the halves out because there's a half on each side. And then I'm going to divide both sides by m, okay? And when I do that, I get v squared equals k x squared over m. And then to get v by itself, well, I got to square root it because right now it's v squared. So if I square root both sides, okay, I get v equals the square root of k x squared divided by m, okay? Now I'm going to do one step further. I have the square root of x squared, which is simply x. So I can pull that x squared out of the square root and just make it an x. And I get the following. V equals x times square root of k over m, okay? All right, so then you did three sets of data. The first thing you graphed is you graphed velocity versus mass, okay? Okay, so looking at this equation here, I'll rewrite it right here. So v equals x square root of k over m, okay? Well, first of all, you did not change, in this part of the lab, you did not change x and you did not change k. You left those constant. So the only thing that was varying was Trevor's mass, and that varied his velocity. Well, first of all, I hope you'll notice that if you increase mass, that's in the bottom of your fraction. So if you increase mass, it's going to decrease your velocity. In other words, the bigger Trevor is, the harder it is to get him going. So that just kind of makes sense. Now, what's the relationship between those two? So we had a whole bunch of choices for mathematical relationship. Well, velocity is proportional to, okay, let's get rid of the x and the k because we're not changing those, the square root of 1 over x, okay? That is a 1 over square root. So you should have selected, and hopefully you selected, when you did your curve fit, that would have been the best one that you should have gotten, was 1 over square root, okay? So that was the first thing you varied. The second time around, you did velocity versus spring constant k, okay? So again, let me rewrite the equation we just got. It's x square root of k over m, okay? Well, this time you're only varying k, and that changes v. Okay, now in this case, the bigger k gets, the bigger v gets, okay? And if we are ignoring x and m because you're not changing the mass and you're not changing the spring compression in this part of the lab, this would have been part 3 of your lab, then when you increase k, your velocity increases, but you gotta be careful. If you double k, your velocity only increases by the square root of that, which is root 2, okay? So the thing you should have picked there for when you did your curve fitting, the curve should have looked something like this, and that was a square root curve, okay? Oh, speaking of which, the previous curve, by the way, I should have sketched that for you, would have looked something like this, okay? So the velocity went down as mass went up. Here, the velocity is going up as mass goes up, okay? The final thing that you did, and this would have been part 4 of that lab, is you graphed V versus X, okay? So again, if I rewrite my equation, you got this, okay? Now, in this last part of the lab, you left K and M alone. You didn't change those. You just changed X, okay? Well, what happens when you change X? Well, if you increase X, velocity is going to increase. How do they increase? Well, it's V and X. There's no powers, there's no square roots, and nothing like that. So they're directly proportional. If X were to double, V would also double. So the last part of the lab, you should have gotten a curve that looks like that, which actually isn't a curve. It's a line because it should be linear. Okay, so the very last part, you should have gotten a linear relationship. So we're going to be doing a lot more of this kind of stuff in the upcoming parts of this unit. So kind of keep that in mind as you go. Hope that was helpful, and hope this helps you on your practice.